In this video, we're going to be looking at different functions, their parent functions, the graph, the table, and just a couple of key features. So we're going to start off with a constant function. So a constant function, the parent function, would be f of x equals k. So this is just when you have like y equals 3. There's just a constant. That's all you have. You don't have an x, you don't have any other variable, it's just a number. So what that looks like is just a horizontal line. So this is an example. The example that I'm drawing is like f of x equals 3 because it's up at 3. So what a table would look like is you would have your inputs and your outputs, and it literally does not matter what you put in. You could put in negatives, you could put in 0, you could put in positives. The output is always going to be that constant. So in this case, it would be 3. Because no matter where you're at on the graph, the output is 3. So some just key features that I want you to be aware of is that it is going to be a horizontal line. Horizontal line. The domain is all real numbers. So that's negative infinity to positive infinity. And the range is just, in this case, 3. Like it's just the constant. So I could have made my example like f of x equals 7, and then all the outputs would be 7, so the range would be 7. But it's just one value. Another function that we have that you should be familiar with is a linear function. And the parent function of a linear function is just f of x equals x. So I know often we think about linear functions, y equals mx plus b. So for the parent function, the slope is 1 and the y-intercept is 0. So you go like up 1 over 1. And I'm going to try my best to... Okay, there's a little bit of a shaky line. It's not supposed to be. So that's the example of a parent function. And one of the things about linear functions is that they have a constant rate of change. And so when you are plugging in values, so in this case, -1 is -1, 0 is 0, 1 is 1. It's going up by the same amount each time because it's a constant rate of change. So a couple of things that you might not have thought of with linear functions is the domain of a linear function is all real numbers all the time. Negative infinity to positive infinity. And the range is also all real numbers. Negative infinity to positive infinity. Regardless of what linear function you have, that's the domain and range. Unless there are additional restrictions put on it, linear functions have domain and range of all real numbers. Another thing that you need to understand, or an important key feature of linear functions, is that it's either always increasing or always decreasing. So we could say that by doing strictly increasing or decreasing. So it can't do both. It can't be doing both. Lord have mercy. It can't do both. It's either always going up or it's always going down. It's not going to go up and down in the same function. So the next function that we want to talk about is a quadratic function. So quadratic functions start out in Math 1, you get them in Math 2 and 3, and now again in 4. The parent function is just x squared. And what it looks like is a u. I'm going to try to draw. This is definitely a sketch. Those are not going to be exact values. But if we look at this, our function, the negative values for the parent function end up positive. and the positive values end up positive. And the reason for that is because you're squaring it. Now, of course, there are transformations that can make this function look differently, but that's how it looks originally. So I want to give you a couple of key features to note about quadratic functions is the domain is always going to be all real numbers, negative infinity to positive infinity. I am going to get to some that that's not true for, so bear with me. The range is going to be restricted for a quadratic. So if it's a U or if you flip it upside down, either way, you're either going to have an absolute max or an absolute min. Unlike the linear function, see how it's going up and down forever, so there is no restriction on the range. For a quadratic, in this case, our lowest point was 0, like it didn't go any further down than that. So your range will be restricted for a quadratic function, but the domain is not. Another thing just to note is that it is a U shape. So all your quadratics are going to look like a U. The next function that we're going to talk about is a cubic function. So a cubic function is raised to the third power. So we would say f of x equals x to the third. And it kind of looks like a little squiggly line here. If we did a table to denote values and have x and f of x. So in this case, the reason it's going to go up and down, unlike the quadratic, is because when you raise something to the third power, it can still become negative because you're multiplying something by itself 3 times instead of just twice. So for example, it would be 2 to the third, which is 2 times 2 times 2, which is 8. If it was a negative 2, it would be negative 2 times negative 2, positive 4 times negative 2, negative 8. I don't know if y'all stuck with me through that, but anyway. All right, so let's look at some key features of a cubic function. So just to remind y'all, the degree is the highest exponent, right? So the degree here is 3. Because it's an odd degree polynomial, the domain is negative infinity to positive infinity, and the range is also negative infinity to positive infinity. So there aren't restrictions on the domain and range of cubic functions. And now that we've gotten this far, I do want to just kind of relate the last 3 functions that we've talked about, linear, quadratic, and cubic. So with your quadratic and cubic functions, you're going to have pieces, generally speaking, where they're increasing and decreasing. Now you can kind of see where the linear function is either strictly increasing or strictly decreasing. There aren't those changes. Often with a cubic function, you'll find a relative max or min. But that's not always, so I'm not going to put in little key features. So the next function we're going to talk about is an exponential function. So the parent function is b to the x, b representing the base. So there isn't an actual like value for b that we're going to put in, kind of like the constant function. But this is what an exponential function looks like. It's got that curve to it. And if you notice, so I'm going to assume like, let's do like 2 to the x or something for my table. If I plug in a negative value, if you think about that, a negative exponent, that's what's happening. You're going to put a negative in the exponent. All it does is it flips. So if it was 2 to the negative 1, it would be 1/2. Let me write that so you can track with me. 2 to the negative 1 is 1/2. So what happens with a negative exponent is you just flip it, and so the value of it isn't actually negative. So if you can see here, the parent function of an exponential function is going to be only positive. So unless there's a transformation that brings it down by either a translation down or a reflection, then all the output values will be positive. So anything raised to the 0 power is 1, if you remember that. And then if you did like 2 to the first power, that equals 2. So we're assuming for my little table here that the base is 2. This is what an exponential function looks like. Now there are 2 different types of exponential functions, exponential growth and exponential decay. I have drawn one that's growth, and we're going to talk about that in just a second. Let's talk about the domain and range real quick. So the domain of an exponential function is always going to be all real numbers. Negative infinity to positive infinity. Because you can put a negative in an exponent, you can put a positive in an exponent, you can put a 0 in an exponent, no problems. The range is always going to be restricted because of something called the horizontal asymptote. Because this negative exponent only flips it doesn't actually make the value negative, like 1/2 is still positive, it's never going to get below that horizontal line. So all exponential functions are going to have a horizontal asymptote. All exponential functions have a horizontal, if I can spell horizontal, asymptote. That'd be too slow sounding that out. All right, the last thing I want to mention about exponential functions is bringing it back to the idea of exponential growth or exponential decay. Like linear functions, it's either going to be strictly increasing or decreasing. So what I mean by that is that it is not going to go up and then down or down and then up. Exponential functions are either always going up or always going down. So the next function is called a logarithmic function. And if you'll remember, that's the inverse of an exponential function. We're going to talk more about this function. It's got a whole unit this semester, but I am going to talk about the parent function, just log of base b, actually, of x. If you don't write look, that kind of looks like a 6. That's a b. If you don't write that, that means it's the common log, and the common log has a base of 10. Maybe that's familiar to you. I hope so. If you had me in math 3, some of y'all are laughing because you're like, yikes, no, it's not going to show. All right, so this is the graph of a logarithmic function. And if we do a table, and I'm just going to use the common log to fill in this table, what happens is you cannot take the log of 0 and you cannot take the log of a negative number. So I could try to do like -1, but that's undefined because you cannot take the log of a negative number. You also cannot take the log of 0. But maybe if we did the log of 1 and it was just the log of 1, not log base 2, it's like the base was 10. That would end up giving us an output of 0. If we did, and I'm just going to make this a little bit easier for myself, if I did like 10, that gives us an output of 1. So if you notice, look at these values of x. They're increasing. The values of f of x are also increasing, right? But not by very much. I went up 10 here and it only went up 1. The next one would be if I did 100, this is only going to be 2. So it is always increasing, but it's just increasing really, really slowly. So the things about the logarithmic function that I want you to remember are some key things. We'll first talk about the domain and range. The domain is restricted. Now, I'm not going to tell you how it is. The one that we just did is restricted from like 0 to infinity, but sometimes that changes based on transformations. If we remember, the exponential function had a horizontal asymptote. The logarithmic function has a vertical asymptote. Now, the range is all real numbers. I also want you to remember exponential and logarithmic functions are inverses. That means that the x's and the y's switch. So that's why the domains and the ranges switch in the way that they do. Another thing I want you to remember, like I said earlier, is they always have a vertical asymptote. Vertical asymptote. And then it's the inverse of an exponential function. It also is only going to be either like strictly increasing or strictly decreasing. That is true of logarithmic functions too. Again, we'll have a whole unit on logarithmic functions. We'll have plenty of time to talk about them. All right, the next one is a square root function. So f of x equals the square root of x. And the way that looks is like a swimmer's arm is how a lot of people refer to it. If we notice, we have x and f of x. For this parent function, if I try to plug in like -1, you cannot take the square root of -1. So this is undefined. If we tried to do 0, the square root of 0 is 0, so we're good there. Square root of 1 is 1. Let's make it easy. Square root of 4 is 2. And so, again, this one is going to be either increasing or decreasing. The domain is restricted, and so is the range. The reason the domain is restricted is because you cannot take the square root of a negative number. So whatever is underneath the radical has to be greater than 0 because it can't be negative. And that in turn makes the range restricted. The last one that I want to talk about is an absolute value function. So an absolute value, the parent function is f of x equals the absolute value of x. And recall that absolute value just means that the distance from 0. So, for example, the absolute value of 2 is 2. The absolute value of -2 is 2. Because both of these are 2 away from 0. They're just in different directions. So, what that looks like is a V when you graph it. The absolute value function looks like a V. Because all those negative values, it would just look like a line, but the negative values become positive, so those flip over while the positive ones stay where they're at. So x and f of x, so -1, 0, 1, 2. So this ends up being +1, 0, +1, +2. For an absolute value function, the parent function that has not been transformed. So you can have a negative value if it was moved down or reflected. So a couple of key features about the absolute value function. First, let's start with the domain and range. So the domain is going to be all real numbers because you can take the absolute value of any number. The range is going to be restricted. And as you can see right here, there is a minimum value right here. So there can be a maximum value if it was reflected, but the range is always going to be restricted on an absolute value function. And then the general shape is a V, so it's a V shape.